If you've ever used a radio, you'll know that when you turn the dial, one radio station becomes loud and clear, while all the others fade away. But the antenna isn't just receiving that one signal, it's receiving all the frequencies at once. So how can the radio pick out this one signal from a tangled mixture and play it cleanly? The answer lies in a phenomenon called resonance. Inside the radio is an RLC circuit, and the dial adjusts a capacitor in that circuit. By changing the capacitance, the circuit responds strongly to one particular frequency, while the others are suppressed. If you're studying AC circuits, you've probably seen resonance appear in equations like this one or this one. But for many students, this can still feel a bit mysterious. Why does the frequency depend on capacitance and inductance, and what is the physical significance of this frequency? Finally, why is this phenomenon so useful in the real world? In this video, we're going to build a clear, visual understanding of AC resonance from the ground up. First, we'll see how inductors and capacitors respond differently to changing frequencies. Then, we'll see how energy can oscillate back and forth between electric and magnetic fields inside the RLC circuit, and how this naturally leads to resonance. Finally, we'll uncover how the resonance curve, bandwidth, and quality factor determine how sharply a circuit can select a particular frequency from a complicated input. By the end, resonance won't just be an equation we memorize. We'll understand what it physically means, why it happens, and how engineers use it to build real electronic systems. So let's begin with a quick recap of how resistors, capacitors, and inductors behave in AC circuits. A resistor dissipates energy as heat. A capacitor stores energy in an electric field between its plates, and an inductor stores energy in a magnetic field around the coil. So instead of permanently removing energy from the system, capacitors and inductors temporarily store it, then release it back into the circuit later. This is reactance, which causes phase shifts between voltages and currents, as we saw in the previous videos. But something particularly interesting happens when we place both capacitors and inductors in the same circuit. Here I have plotted a sinusoidal voltage input and an arbitrary current, which depends on the capacitor, inductor, and resistor. If we visualize the electric and magnetic fields within our capacitor and inductor, and go through each cycle, we can see them grow and collapse like so. Now, the times at which they grow and collapse depends on quite a few things, which we'll talk about later. So for now, let's just establish that the circuit contains a continuous oscillation of energy between electric and magnetic fields, as well as some dissipation through the resistor. I now want to demonstrate what happens to the currents as we vary the frequency of our circuit. The frequency omega is completely determined by our AC voltage generator, so it is unaffected by the circuit components, at least when the system is in steady state. As we vary it, we can see the currents change like so. Here is the current for a high frequency, and here it is for a lower frequency. The most interesting thing is that, besides the amount of oscillations changing, the amplitude of the current is also changing. The current magnitude depends on the frequency. Let's plot the current magnitude against the frequency so we can see this more clearly. At low frequencies, the current magnitude starts low, then rises fast. It then reaches a peak amplitude, then steadily decreases for higher frequencies. Before explaining the significance of this effect, let's figure out why this is happening. For this, let's recall how the current relates to the voltage. In this series circuit, V is I times the impedance, Z. The impedance is the total opposition of the circuit to the current. As we saw in video 5 of this series, in our RLC circuit, this is equal to the square root of the resistance squared plus the reactance squared. In an RLC circuit, the total reactance is the reactance of the inductor, XL, minus the reactance of the capacitor, XC. The reactance of the capacitor and inductor work as follows. An inductor, fundamentally, resists changes in the current, because when a current flows through it, it builds a magnetic field, which requires energy. The faster the current tries to change, the more strongly the inductor opposes it. This means that inductors resist high-frequency signals more strongly than low-frequency ones. In other words, the reactance of an inductor scales with frequency, where XL is simply omega times L, the inductance. So the inductive reactance increases linearly with frequency. Capacitors, on the other hand, behave in the opposite way. A capacitor resists changes in the voltage because the electric field takes time and energy to grow. When the voltage is changing slowly, it takes time for charge to accumulate on the plates, so the capacitor strongly resists the current. But when the voltage changes rapidly, charges only need to move small distances, and the capacitor allows current to flow more easily. In other words, the capacitive reactance decreases as frequency increases, where Xc equals 1 over omega times C. So as we sweep through frequency, the behaviors of inductors and capacitors move in opposite directions. So let's plot the reactance as a function of the frequency as well. Here are the values of XL and XC separately for reference. At low frequencies, we can see the capacitor dominates the circuit, while at high frequencies, the inductor dominates. But most interesting of all, we can see a frequency where the reactance drops to exactly 0. At this point, the two reactances are exactly equal, so cancel out. Therefore, the total circuit impedance also minimizes, and as you can see on the current graph, the magnitude is now maximized. It is at this frequency that resonance occurs. We label this point the resonant frequency, omega naught, and there are many interesting features of it. As you can see on our voltage versus current graph, the phase shift has dropped to 0, and if we plot the power, we see a completely positive power curve. Meanwhile, if we vary omega, we can see that we get some negative power, which, as we discussed last time, is energy flowing back into the source from the electric and magnetic fields. So what is happening with this at the resonant frequency? Well, at this point, physically, the energy stored in the electric and magnetic fields is flowing back and forth between one another in perfect synchrony, such that all the energy provided by the source flows straight through the resistor, hence the positive power curve. Now this is neat, but you might be thinking, well, what is the point of it? After all, why bother having a capacitor and inductor in the first place if our goal is just to cancel their effects out? Well, this circuit has some very useful applications. Imagine instead of a single AC voltage source, the current is driven by a signal containing many frequencies at once. This is exactly what happens in a radio antenna. It picks up electromagnetic waves from many different transmitters, producing a voltage signal that contains all of those frequencies combined. If this input was attached only to a resistor circuit, any frequency of voltage would pass straight through the circuit, and the current would look like so. This isn't very useful. However, if we add a capacitor and an inductor, the circuit behaves differently. Here is a current that could appear in an RLC circuit from the same antenna input. As you can see, it is a neat sine wave with one standout frequency. This has happened because in an RLC circuit, the current amplitude depends strongly on the frequency of the input signal. So, we see the current responds strongly to a small range of frequencies and weakly to others. Here is the current magnitude and reactance as a function of frequency for this RLC circuit. As you can see, the current is amplified near the resonant frequency and diminished for the other frequencies. The current you are viewing on the left has this resonant frequency. In other words, the circuit acts as a frequency filter, which is exactly what we need in a radio. The antenna picks up signals from many radio stations at once, but the resonant circuit allows us to isolate a very small range of them. But here's the most interesting part. Imagine we can directly control the resistance, capacitance, and inductance of our RLC circuit. If we were to vary the resistance, this is what happens to the current for the same voltage. As you can see, the peak simply decreases as resistance increases, and vice versa. Now, if we animate the capacitance changing, we can see the resonant frequency changing, while everything else stays the same. You can see that, as we do this, different frequencies of the input waveform are being detected. Finally, if we alter the inductance, we can see the peak move, but we can also see the peak width widening simultaneously. In a radio, the dial usually controls the capacitance of the circuit, because changing capacitance allows us to change the resonant frequency and nothing else. It does this by simply varying the plate distance between the capacitor, if you are curious. So why is all this happening? To answer this, we want to know how our resonance curve relates to the resistance, capacitance, and inductance. Let's see if we can derive this. For now, we'll forget the radio example and focus on the resonance curves of a generic RLC circuit. Looking first at the reactance of the system, the total reactance is the difference between the inductive and capacitive reactances, i.e. XL minus XC. Resonance occurs when these two quantities cancel each other. Substituting in the expressions for each, and setting omega to omega naught, we get omega naught L equals 1 over omega naught times C. And we can rearrange this for the resonant frequency to obtain omega naught equals 1 over square root L times C. So, if we increase or decrease the inductance or capacitance L or C, we can decrease or increase the value of omega naught. Let's quickly visualize this happening. First, varying the capacitance, we observe this. And if we vary the inductance, we see this. In both cases, the resonant frequency moves. But you may see that the curve changes a little differently when we vary the inductance compared to the capacitance. Inductance also widens our resonance peak. Now, as we said earlier, the RLC circuit does not necessarily cut out all the other frequencies beside the resonant frequency. If the peak is wide compared to its height, it doesn't really matter what the resonant frequency is, because we can't even distinguish it from the other frequencies. We can see this here as we vary the resistance. So the width of the peak matters too. Let's enlarge our current graph so we can see this clearly. We measure the width of the peak by defining its bandwidth, delta omega. We define the bandwidth as the width between the curve for the current that corresponds to half the maximum real power output of the circuit. The maximum real power output occurs at the resonant frequency, as the reactance at this point drops to 0. We'll denote the half maximum current on our current graph as IP over 2, and write these two frequencies as omega 1 and omega 2. So what is this half power current? Well, considering the full power current, we know all the power is going through the resistor. So the power P equals the maximum current squared times R. This maximum current in this context is the RMS current of our circuit. We discussed this in a previous part. So to get the half power current, we can multiply our equation by a half and see clearly, given R is constant, that the current must be IRMS over square root 2. We define a final quantity, Q, as a quality factor of our RLC circuit. This is the ratio of the resonant peak and the bandwidth, which is basically a measure of how distinct our resonant peak is. A high quality factor means the peak is way larger than the bandwidth, and a low quality factor means the peak is small compared to our bandwidth. You can see this changing as we vary the resistance. So let's see if we can express the bandwidth and quality factor in terms of R, L, and C. The bandwidth is the difference between omega 1 and omega 2, which are the frequencies when the current is IRMS over square root 2. Using Ohm's law, we can say that any current is equal to the input V over Z, and for our half power current, Z is the square root of the resistance squared plus the reactance squared, as the reactance is not 0. However, for the maximum current, we know the reactance is 0, so applying Ohm's law here, we find it's just V over R. Now we also know already that the maximum current is square root 2 times larger than the half power current. So if we divide our second equation by square root 2, we can write this as I half P equals V over square root 2 times R. We can now equate these two results and cancel out the voltage term, leaving square root 2 times R equals the square root of R squared plus X squared. We can simplify this by squaring both sides and rearranging to get R squared equals X squared. This equation is true when the frequency is equal to omega 1 or omega 2. So we'll write the reactance in terms of the frequency. if we square root both sides, we get plus or minus r equals omega L take 1 over omega C. Multiplying by omega, we get this neat quadratic where 0 equals omega squared L minus or plus r times omega minus 1 over C. To find our frequencies, we can write out the quadratic equation like so. You'll notice that we now have 2 plus or minus parts. This means that there are actually 4 solutions to this, which we can write out like so. However, we can clearly see that our frequencies have to be positive. Out of these 4, we know this one is going to have to be negative. And we can also see that this numerator will be negative, because this r is always going to be smaller than the square root of r squared plus 4l over c. So, we are left with these equations for omega 1 and omega 2. As we said, the bandwidth is simply the difference between these, which happens to cancel out very neatly. We obtain a bandwidth of r over L. And this matches what we saw earlier, where the resistor and the inductor vary the width of the curve, while the capacitance does not. So all in all, we can define the quality factor, the ratio of the resonant frequency to the bandwidth, as r over square root LC times L, which simplifies to 1 over r times the square root of L over C. So with this, we now have a full toolbox for controlling our resonance curve. In applications like our radio example, each radio station has a set of frequencies it operates at. So we have to find a balanced quality factor. Too low a quality factor means too many frequencies are included, while too high a quality factor means too much will be filtered out. And with that, let's now summarize what we've learnt in this video. Firstly, we can achieve resonance in a series RLC circuit when a capacitor and inductor reactances are equal. In this state, the current is maximized, and all the power is dissipated through the resistor. The resonant frequency for an RLC circuit is 1 over square root LC, and we can use this to select a frequency or range of frequencies from the input. Plotting the maximum current against a frequency, we find that we can control not only the value of the resonant frequency, but also the width of the peak, called the bandwidth, which occurs at the half power current equals I RMS over square root 2. The bandwidth is equal to R over L. We can define how distinct the peak is using the quality factor, which is the ratio between the resonant frequency and the bandwidth, and in terms of R, L and C, we find this to be 1 over R times the square root of L over C. So overall, we've built a signal filter, which we can control by varying these parameters. This will be the last video in this series on AC electricity for now, but if there is something you really want me to cover, do leave it in the comments section below, as I may get around to it in the future. By the way, I will soon be releasing practice problems for this video on the free Decipher Physics iOS app, which already contains practice problems on capacitors and GTC physics. Thanks for watching.